How about maybe down the corner?
Yeah.
Would that work?
Sure.
I prefer to have this a little bit open because of the recording.
Oh, yeah.
What is it recording?
It is recording you and me. Well, not you, but mostly me. But it is recording your voice. So. Everybody had no difficulties finding the recording of the lecture on Elaeum and all related material? Everybody can access Elaeum?
No.
No?
Yeah.
Not yet.
Okay, but
I'm
it's
gonna
because,
arrange
yeah,
that.
okay, good. If not, send me an email, I will send it to you personally, yes, all the information. Okay, well, again, series of steps, and then I propose to follow the series of steps as well as we can throughout all the exercises. All right, so, last time we derived two rules. One of them was time dilation, the other one was Lorentz-contraction, and both of them came about because apparently there's a postulate in physics that says the speed of light should be the same value for all. And as we discussed during the main lecture, if you want that the speed of light is the same for all, that means if you're going to measure the speed of light in the amount of distance divided by the amount of time, then something's got to give, yes? You cannot have the same delta x's and delta t's for both observers if the answer, the ratio should come out the same. And this is really, that's all there is to it. The rules, if you remember, were the following. So you have delta time equals gamma some other delta time. Remind me, did I use capital deltas?
Capital. You use capital.
Okay.
But
You know,
use
yes.
small is infinite.
It's infinitely small, right? And you remember that one point that I made was you can also use this rule when you're looking at things that are accelerating with respect to you. And then you will have to integrate. And for integration, you need infinitely small ones. Now, when I do physics, I never think about capital, the big deltas. So I might be sloppy in my notation, but we all mean the same thing, just a certain amount of time. So let's stick to those. I have two dt's here. If this were Newtonian physics, those would be the same values for all observers. It's not Newtonian physics. It's relativistic physics. That means you have two of these. One of them I'm going to call from now on the tau. And that's because that is the official notation. I didn't use it during the main lecture, but we will use it extensively next week onward. Question to you. Two things happen. Which of the two observers measure dt and which of the two measures d tau? Let me be a little bit more clear. Do you remember what an event was?
Yeah.
Okay, tell me.
So you have like one fixed
Yes.
frame referential,
Yes.
and another one that is like moving out.
That's good. That's correct. Those are the reference frames. Now, things happen in nature.
Yeah.
Okay? And to do relativity, we need something that is called an event. We have to be very clear. That's going to be one of my steps that I'm going to write down in a moment. But we have to be clear on what you understand with what I mean by the word event.
An event is everything that happens in a specific time, in a specific place.
Exactly. Exactly. So something that happens, and in my mind I always take exploding firecrackers because that sort of approximates an event. It happens at one place. Yes, sure, the explosion, you know, all the shrapnel flies in all directions, but the explosion happens at one place. And it happens at one time. And yes, if you zoom in, then it will take a certain amount of time, a very small amount, but ideally an event is something that happens at one location in space at one moment in time. Okay, so suppose that you have two events happening. It's very important because relativity doesn't say anything about one event. It always makes statements about two events. One thing happens here at some moment in time, one thing happens here at some moment in time. There's an amount, a certain duration of time in between the two events. Exploding firecracker, another one takes 2 seconds before the other one goes off as the first one has gone off. And it also takes a certain amount of space. There's 2 meters in between them. Okay? The only thing that relativity does statements on is the duration between two events and the distance between two events. It doesn't say anything about one event or the other event, it only says something about durations and distances. So you will always find these or deltas. Not all books and not all literature is very good at emphasizing this. You might find books where they just omit the these altogether. And it gives you the impression that relativity then apparently says something about this one particular event and this one particular location. It doesn't. Okay, so you have to be clear, very clear about these things. So this is why I'm emphasizing this. Okay, 2 exploding firecrackers. Bang, bang, 2 events. Now, suppose I was standing next to one firecracker, this one explodes, and well, where you're sitting is where the other one explodes, bang, bang. It's safe, don't worry about it. 2 exploding firecrackers. You and I are watching these 2 firecrackers, and there's some other person walking along. Could also be the other direction, that direction, but he's moving with respect to us. Suppose that you and I say that the 2 firecrackers explode 2 seconds after each other. The duration between the 2 firecrackers is 2 seconds. Now, the moving person will also see these 2 explosions and will come to a different conclusion, a different number for the duration. Who of us, well, you and I are going to measure the same thing, but this next person, which of the 2 is going to measure which of these amounts of time? Yes?
So the guy who is moving will be the toe, and the guy who is standing will be...
What is moving?
Like, if we have the 2 evens,
Yes.
the guy that is moving towards, like, one that relatively to the guys, like, standing. So if we say that dt is at the time I measure, if I'm sitting, the toe will be the time...
Wasn't it the exact opposite?
No.
Here we see the first confusion already, yes?
Because it was like whoever is like measuring it at the same point for the 2 events is the one where the tau was.
Yeah, but if I'm standing over here
Yeah.
and the other one is exploding over there, then I'm not seeing them at the same location, yes?
Oh, yeah.
So that's the
And
Yes.
yeah,
So you have to be. This is where most of the confusion in relativity comes from at this stage. Trust me, there will be more confusion as we go along. Okay, but the confusion at this point is, I can imagine, typically is where do you put the gamma? Who gets the shorter and the longer version? So I want to be very clear about that. We talked about this on Tuesday. This d tau is the duration between 2 events. So this is not new information. This is me summarizing last time. Duration between 2 events for the frame, the reference frame, in which the events, oh, it's such a long sentence, but you know what I mean, which events happen at the same location. There you go. This is the other guy's amount of time between the 2 events. This number comes out shorter. Excuse me, it comes out bigger. And that means if the other person is looking at the 2 events, he will see more seconds pass between the second event happening. That's another way of saying that apparently what he's seeing is happening in slow motion. Yeah. Now I want to be extremely clear, and I will emphasize this as we're going to make the exercises. This is not a statement about light first having to reach the guy before he sees things. That effect also exists. Yes, if something happens here and something happens over there, then that thing happening over there takes longer to reach my eye before I see it happen. But that's not the statement here. I'm actually saying whatever happens there has happened after more seconds. The whole travel time of the light has nothing to do whatsoever with these equations. That effect does exist. This is the Doppler effect. Yes?
Yeah.
Okay, so yes, that effect exists, and if you want to really do exercises and put all the details in, then you have to take that into account as well. You get something called the relativistic Doppler effect. The fact that it happens later there than for that person there, and the fact that the time that still has to travel towards you, gives you the relativistic Doppler effect. Not going to bother with this. We're just going to make a statement about what happens and how you measure that, and the travel time we're going to leave out for now. Okay, so this is the other guy's time. Second statement, we saw that there was also a Lorentz contraction, and I went with the opposite gamma. And just to get the notation more, call this L0. It's called the proper length. You just have the nomenclature right. D tau, because it is this one very special observer for whom two things happen at the same location, it gets its own name. It's called the proper time. It's just this statement, but with a name attached to it. So tau is called the proper time, and it's going to be extremely important from next week onwards. It's also called eigentime, depending on whose literature you're reading. I'm probably going to use both of them as much as the other. Okay, so that's good. Now let's go to the Lorentz contraction. The idea is you look at something and you want to measure its length. Now, this equation only applies if one of the two reference frames sees the two things happen at the same time. Can you guess under what condition this one? Sorry, at the same location. This only you can only use this equation at the moment that you see things happening at the same location, one of the observers. And that observer, that amount of time is this eigentime, this proper time.
Same time then.
Yes. Just out of almost like out of symmetry, you can sort of guess, well, then I guess one of these lengths should be measured at the same time. If one of these durations has to be measured at the same location, then maybe one of these lengths has to be measured at the same time. I'll make this explicit next week, but I just want to already tell you that it is the case. Can you guess which of these two lengths have to be measured at the same time?
L0.
Yeah.
L0,
yeah? Why would that be? Because I put a 0 there, okay.
Because it's from the resting frames. It's
bigger.
like, it's the resting distance.
I hear lots of semantics arguments. Well, because it's contraction, so it must be such and such. Well, that's all true. But that's after the fact, yes? Let me rephrase the question more visually. Suppose that a stick is flying by. You know, let's actually make a stick fly by.
Wow.
Can you I'll put it back in a second, okay? Suppose that there's a stick flying by. There you go. Yeah. Okay, and I want to measure the length of the stick. Now, I can identify at least two observers, two reference frames. One reference frame is, that will be me right now, walking along with the stick. And I measure how long the stick is. Now, how do I measure a length of a stick in the first place? I'll come back to that in a second. It's very important for our story. What I could also do, I'm not going to, but I could throw this thing and watch it fly by. Alright? Now, two reference systems, and one of them measures L0, the other one measures L. And I want you to understand which one measures what, and in order to do so, you have to understand how do you measure a length of something in the first place. And it's very simple. You measure where the front end is, you measure where the back end is, those are two events, locations in space, and you subtract their locations. What you end up with is, yeah, okay. You want to know how tall I am, measure where my feet are, where the end of my head is, the difference between those two. Now, one of these two observers has to do the front end measurement and the back end measurement at the same time, otherwise he will get a crappy number.
Yeah.
I throw this stick in that direction, I'm not walking along with it, and I want to measure how long the stick is. I measure the front end, I wait 2 seconds, and then I measure where the back end is.
So the observer that is moving along with the...
Yes. What about him?
Yeah, he saw it.
He's
at
the only
same
one
time.
that can measure in the same.
Same time frame.
Yeah.
The guy who's moving along,
Yeah.
he can measure whenever, right?
Yeah.
If he measures the front end and he waits 5 seconds, measures the back end, in his frame,
It's always the same.
it's always going to be the same number. So that guy doesn't matter. The guy who's seeing the thing move, he has to be sure he measures the front end and immediately measures the back end, because if he waits a second, the back end will have
But
moved.
how can he do that?
Oh,
The only one who can measure in the same time would be the one who is carrying the stick.
No, absolutely not. What I could do, for instance, is that I have some magnetic thingy here that activates a firecracker that happens here. Yeah, and at the moment that it passes, a firecracker goes off, and I measure where the firecracker went off. And I also have a firecracker over here, and that one also explodes, and I have a beautiful measurement of the back end and the front end.
So do you create two events at the same time?
Yes.
Or?
Now, the events here, I mean, I'm putting it in terms of firecrackers, but I could simply say measuring front end and back end. How I do this in practice, that's a whole different story in itself. But you can do a measurement. I mean, I try to put it in firecrackers. But there's in principle no difficulty measuring a front end and a back end at the same time. Maybe you say, well, wait a minute, by the time you're looking at that, where that thing is, you're not looking at the back end, and you have to move your head, and then the thing has already moved, and you're already too late. Okay, I ask a friend to measure where the back end is. Okay, you can measure front end and back end at the same location. You have to think about how to do this practically. But one thing is certain: if I look at the moving thing and I want to know where its front end and its back end is, I better be sure that I measure it at the same time, because if I wait a second, then where the back end is then is not a statement about the length of the thing anymore.
Yeah.
So that means, and I will put this back. There you go. So that means that in order to measure a length, one of the two observers has to be sure that he measures the front end and the back end at the same time. Now, which of the two is that?
The one that's standing still.
Yeah, standing still.
I mean, not in the reference of the.
Thank you. No, yeah, exactly. You mean standing still with respect to the Earth or something like that? Okay.
Yeah.
Okay.
With respect of
the guy who sees the stick move.
moving, yeah.
That's the guy who has to measure at the same time.
Yeah.
The other guy doesn't matter. So just as this only applies when one of the two measurements, or excuse me, one of the two reference systems measures the time at the same location, this one only applies when one of the two observers measures the length at the same time. It's very important. Now, L0 is the amount of length that the guy measures who runs along with the thing. So this thing is what we call the proper length, or less common, but you can also find this, the eigenlength. Is how long the thing would have been if it would not have moved in your frame. And this is how long the thing will be if you did see the thing moving. And this is their connection, 1 over gamma in between. Okay. And again, just repeating myself, this first one, time-dilation, can only apply when at least one of the observers sees the two things happen at the same location. This one you can only apply if one of the two observers measures length, front end and back end at the same time.
And that one would be L, not L0.
Exactly.
Okay.
The guy who measures the front and the back end at the same time would measure L.
Okay.
Okay.
So again, he gets the gamma, because then we...
Yes. Yes. Now, I don't really mind how you remember it, but you do have to remember this, because this is where most of the confusion lies in doing these exercises. All clear so far? Okay. Now, I promised you a series of steps. As in, if you follow this, then at least you have a very good handle on what you should at the very least do to make these exercises as confusion-less as possible. And then you might have to be ad hoc here and there. But let's write down the general rules. First of all, and it's very important that people tend to forget, identify the two events. Two things happen, because that's the only thing that relativity does statements about. It doesn't say about one thing or the other thing, it says about their two things and their duration and distance. Identify which of the two things, or which two things you're looking at. So step one is identify the two events. And immediately a warning, there are situations where the two events change throughout the exercise. We will see an example in a moment, okay?
There was also exercise with 3 events.
Yes.
That's
Yeah.
possible.
Yes, absolutely.
Okay.
In fact, again, some exercise we will see in a moment regarding spaceships and such. Okay? So identify the two events and mind that these two events might change as you progress through the exercise. Now, the simple exercise only has 2 events. The more complicated ones, so mind that these might change. Secondly, also extremely straightforward, but be mindful of which reference frames you're looking at these two events. You can have two things happening and looking at them from different reference frames, and you have to identify, well, which reference frames are we looking at in this particular example. There's usually 2 reference frames in an exercise. There might be 3, there might be 15, depending on what the exercise is. But you have to identify which one is which, otherwise you have no idea what you're doing. You find the delta t, but you have no idea, is it this guy's delta t or the other guy's delta t? In order to keep that really clear for yourself, you have to first identify which reference frames are there in the first place. So identify reference frames. And again, these two might change as you progress through the exercise. Next step, check whether you are allowed to use these formulas. We wrote down under what conditions these formulas can be used in the first place. Right? One of your reference frames has to see the two events happen at the same location or at the same time. If that is not the case, these will not work. Now what do you do then? See next week, because I will give you the general rules from that moment on. But for now, we're going to stick to these. So check whether time dilation, that's the first formula, is allowed. And or whether Lorentz-contraction is allowed. If the answer is no, and I will put this between brackets because we haven't officially seen it yet. If the answer is no, go to Lorentz transforms. And I will introduce those next week. If not, use the Lorentz transforms. And I think I already told you during the main lecture on Tuesday that the Lorentz transforms are the general case, of which these two are only two very particular examples. Now again, I cannot promise that all exercises will become easy if you do this, but it's the very least you should do. All clear so far?
Yeah.
Do an exercise? Yes.
I have a question.
Yes.
So the L0 is the one, the guy who's moving with the stick.
Yes.
And L would be the one who's actually standing still and looking at the stick, right?
You have to be careful when you say standing still, because you can only say that you stand still with respect to something.
With respect to the Earth, then.
Yes, but the Earth itself is not standing still with respect to the Sun. So,
It's a guy
in
with
effect,
respect to the moving ladder. Yeah.
No, but he's also not standing still with respect to the moving ladder.
If there's a stick on the table and you move by it, it's moving for you relatively. So then you're
yes
the one who sees the thing happening in a different location.
Yeah, but then L varies accordingly to when he actually measures the front and the back end, right?
What I'm saying is that if you want to measure L, and I know exactly what you mean, but I want you to be sure about the way that you phrase it.
Yeah.
You cannot say, well, L's the guy who is standing still because it is the stick that is moving. There's no such thing as saying one guy is certainly moving the other. You only can say that they're moving relative with respect to each other, yes? What you mean, and I think your understanding is correct, but your phrasing should be a little bit more crisp. What you mean is that this is the observer, L0, for whom the stick is not moving. And this is the observer for whom the stick is moving.
Yeah.
Now, which of the two observers is really moving is a question that simply is indeterminate in relativity. So yes, this guy is the guy for whom the stick is, who sees the stick move.
Yeah.
Okay, and that guy has to make sure that he measures the front and the back end at the same time. That's it.
Oh, okay. But and if he does, then L and L0 are the same.
No.
What do you mean if it does?
If he does measure the length
No.
at the same time, there's still contraction.
No. There's always, then there's still contraction.
Ah, okay.
No, what I meant was that if you have identified for whom the stick, for who is the guy who has to measure the front end and the back end at the same time, you will still have contraction. The only condition that I meant by that was, then you're allowed to use the formula in the first place.
Okay.
The only way that L is going to be equal to L0, for this you have to remember what gamma is. And gamma is, we derived it on Tuesday, is this. And the only way that this is equal to 1, so if this is equal to 1, then L is equal to L0. So the only way that the two observers will measure the same length of stick is when their mutual velocity, how fast one observer is moving with respect to the other, is 0. That's what we call by V. If V is 0, then all gamma just becomes 1, and then L becomes L0. But that's fairly obvious, right? Because if the stick is simply not moving with respect to you, but you do have two observers, one sitting on the stick and one standing next to the stick, then both of them are not moving with respect to the stick. So of course they're going to measure the same length. But you will always have Lorentz contraction if they are moving with respect to each other. So what I meant again, just emphasizing one more time, the only thing that I meant by checking whether there's one observer who has to measure front end and back end at the same time is whether you can use the formula in the first place.
Yeah.
Okay.
If he only can measure it in one time, at the same time, right? Because also L0 can measure the two events at the same time, but he also can do it in different.
Yeah, of course.
But L is obliged only to.
Yes.
Okay.
Yes. It's good we talk about this because this is very important. This is where most of the confusion comes from. All right. Let's apply this stuff. I propose let's start with a simple exercise. That's 4.1. What I tend to do is that I go through this exercise and I just ask you for suggestions here and there. Is that good? There we go. By the way, if you found a copy of the book, I made scans of the exercises. That I'm allowed to do. I'm not allowed to put the whole Pirate Bay link on there, right? So, okay, but I never heard that. I'm sure that it is.
What about the answers to the exercises?
We can do two things. The book itself has, at the end, has for the odd exercises, gives you the answers. Not all of them, but most of them. But it only gives you the answers. It doesn't tell you how they got there. I write out my solutions. But you can imagine that I'm a little bit hesitant to put all of my own worked out thingies there because I'm a little bit afraid that with all the busy lives everybody has, that people think, you know, I'm just going to read how the other guy did it, and if I understand it, I feel that I've done my work. And this stuff you only pick up by trying it yourself and hopefully get stuck, and then see the answer.
Yeah.
Because then the retention is much bigger than if you just look at somebody else who does it. So I have this great uncle who's 90 years old, who likes to do these, what do you call these things in English? These puzzles in the newspaper where they give you some strange description. No, it's not a crossword. What's that? I don't know. In Dutch it's called a cryptogram. Cryptogram. So they give you some sort of.
Oh, and then you have to write out the words and then you rearrange them to get another word.
Anagram?
But they give you some vague description of something, and I always find it extremely difficult to understand what they really mean. But when then somebody else tells me what it is, I say, oh, well, now I see, now I understand.
Like they give you a hand and then they say minus the or. Is it that? Like
no,
they give you a picture?
I think that's different still.
You have like a description of something, like I don't know. It tells you it's a green round object that you can eat, something.
Yeah, exactly.
And then they give you the amount of letters attached. And you write down apple or whatever it is, or avocado, depending on the number of letters that are there.
It's green and red.
And then there are some of the boxes have numbers.
Yeah, and then you rearrange them with the new word.
And then if you send this final word to someone, you might get some money.
The whole point of this example was that I always find these things extremely easy when my grand uncle tells me what the answer is, and I just have to check whether it fits the description. But the other way around was much more difficult. And I am a little bit hesitant to give you my answers. So you just only have to check if you understand why it is true, as opposed to having tried it yourself first. So let us think about it for a bit. You can find the numerical answer to the odd numbered questions in the back of the book. I'm guessing that maybe by the end we get to the exam-ish, that maybe I will upload a couple of my answers, yes? But of course we're here to discuss these things. So let's just start. Exercise 4.1 is on time dilation. And this one is quite straightforward, but let's go through this. It says, you have a clock moving at 4/5 the speed of light and passes our clock when both clocks reach t is 0. Now you don't have to, but sometimes it pays, especially if you're new to this stuff, to make little drawings. This is a clock, and it's called the A clock. And here's another clock, called this B clock, and they're moving with respect to each other with 4/5 the speed of light, so there you go. And they also say at the moment that clock B passes clock A, this is when both of them reach 0. Alright, fine. When the moving clock reads 24 seconds, so they both read 0, at some point this one reads 24, the question is, what does this one read? Now,
no, wait, can you say it again?
Yes, absolutely. At the moment that this clock, it's moving past, at the moment that this clock was here, both of them have on their display 0. And at some point later, this one, clock B, will have 24 on its plate, its face. Then the question is, at the moment that this one reads 24, what does this one read? Now, Newtonian physics would say, oh, 24, right? A certain amount of time passes for one clock, it must be the same amount for the other. But we're not in Newtonian physics anymore. So that means we have to think a little bit more. Okay, what are the two events?
Two events is t0, t is equal to 0.
Well, wait. What you give me now is a moment in time, but an event is in time and in space.
The two events is when B passes A at t equal to 0.
Yes. So B passes A.
And the second event is when B is far from A and measures 24 seconds. When when B is far from A and measures 20 seconds.
Thank you. This is step 1, yes? Yeah, identify the two events. Event 1 is, again, it's a location and then it's a time, a moment in time. Location is here. The time is 0 for both clocks. Event number 2 is, this clock at some point is here, yes, that is some location, it's unidentified. We don't need it, we can calculate it later if we want. And it happens 24 seconds later, as seen by this guy. Okay, so we know our two events. We also know our two reference frames, right? The guy standing next to this clock, A has a reference frame, that's us, and there's this clock, also has a reference frame. Trick question, who of the two is moving?
Both are moving with respect to the other.
Of course, yes. It depends on who you ask, yes? If you happen to be clock B, then you see clock A move in that direction with 4/5 of C. And if you happen to be clock A, you would say, no, the other guy is moving. So who's moving? Yeah, it depends on who you ask. Both of them are correct. Yeah, but who's moving with respect to the Earth? It doesn't matter. Okay? The Earth is not the reference system. The Earth is not the place from which you have to measure things. High school children think this. We don't. I love high school children. But they make mistakes. A lot. Okay, so we know our reference frame, we know our events. Let's do our check.
Yeah, so B sees the two events happening at the same location.
Yes. So you're making two statements now. What you're saying, first of all, that we are allowed to use time dilation in the first place, because there is an observer, a reference frame, at which the two events happen at the same location. And you made a second statement, all in one, wrapped in one beautiful sentence.
Which is B.
Which is B. That has to be very clear. Is it clear to everybody that the two events, this and this, happen for position, for guy B at the same location? Yeah. So what I always think is, well, supposing he has this huge reference frame attached to him, at which he is always at location 0. He's at the center of his own reference frame, he walks along. Reference frame walks along as well. At the moment that he passes this at his location, well, that was at my position 0. 24 seconds later, oh, that also happens at position 0 in my frame. Not the other guy's frame, but his frame, yes. So yes, we can use the rule, and we know exactly which one is the proper time. So yes, we can use it. So we have, here, being already messy with my deltas, forget about that, okay? So that will be will be this. And now you put in the numbers. 4/5 of C, what is gamma?
Okay, yes.
Yes, thank you. The answer is going to be 40 seconds. You're right. You didn't get it? Well, Elise is filling in these numbers. This number is 24 because B reads 24 seconds. So the amount of time between this event and this event, as seen by B, is 24 seconds.
3/5 gamma.
That is gamma, exactly. If you take your V and you put it into your equation of gamma, you do the math, you find 3/5.
Yeah.
Are you sure? Is it not 5/3?
No, 5.
Yeah, because it's 1 over...
3/5 is going to be smaller than 24 inches.
Yes. And then you multiply this out, you get 40 seconds. So that's all there is to it. So if you just identify who is measuring what, you should be fine.
But Gideon,
yes.
One question. You said that they both move relative to each other,
yes.
right? That means that the events that happen in B can
yes.
also be happening at A.
Yes.
So then you would apply gamma to delta TA if you were in A.
So this is called the twin paradox that you're talking about. Because what you can also say is, but wait a minute. If I were to read what happened at A, and then I would do my two measurements of 0 seconds and 40 seconds, because this is what measured by A, and I measured at location A, then that means that the proper time would have been measured by this one. You would apply the same formula, but now the gamma will be at the wrong side.
Yeah, that's the question. Yeah.
That is, I know. Because as seen from this guy, you might as well say, no, it was the other guy whose time has to be dilated, has to be bigger. Has to be bigger still. So this guy measures, wait a minute, there's 40 seconds between these two events. And then you can ask this guy, if you know that it's 40 seconds between these two events, how much should it be on this guy's clock? You would take the formula again, but now, because you're now basing your calculation on what he saw in his own frame, now this has become 40 seconds. Another gamma will become bigger still. So, something wrong, something fishy is happening, yes? This is why week 3 is on paradoxes. This is one of them.
Okay.
I can tell you that the answer is correct that we write here. Do you want a hint, or do you want to wait until?
I go.
Okay. And I cannot resist giving a hint anyway. It has to do with the fact that one of these, in order to have them move with respect to each other, at the very least one of them must have accelerated with respect to each other. Yes? You cannot build up a velocity of such and such if you haven't accelerated at some point in time.
Yeah.
And acceleration breaks the symmetry. There's a certain symmetry here that you can apply the time dilation formula as seen from this guy and from that guy. So as the way that we wrote it down, it seems as if both of them would go. But if you take into account that one of them must have had accelerated at some point in the past, then all of a sudden one of these two is not allowed to use that formula anymore. That is the short version. The longer will come on Wednesday.
Okay. But how can we use the time dilation here with respect to A, because A doesn't see the two events happen in the same time, in the same location?
No. There's a second way that you can solve the paradox. One of them is by saying, well, one of them is not allowed to use the formula in the first place.
No, but I was not talking about that because.
Yes.
So, like the only way that A can actually see two events happen in the same location is if B goes back to A in some way, returns to A. But here B is moving away, so.
Oh yeah, but
you also changed the event, right?
Yeah, exactly. This is what Rodrigo was really talking about. He said, well, he didn't put it in those words, but the idea behind his question was that these 40 seconds that person A measures to have seen this one reach 24, for this guy does happen at the same location. So all of a sudden you get two new events.
Ah, okay.
The new two events are when clock B passes A, and then the second event is when clock A measures 40 seconds. That is not the same event as when this one measures 24 seconds.
Yeah.
So that's that point. If you take that into account and you redo your calculation, you will find that there is no paradox. So there's two resolutions to this twin paradox, but again we will do this in full detail.
So it's two other events.
Yes. You have switched events, and if you take into account how the events have switched, you will find that there's no difference. And apart from that was my original argument, one of them wasn't even allowed to use this equation in the first place because of acceleration, which we haven't looked at yet. So this is the short version. Longer version will come later, and the period 5 general relativity, but long story. So this is it for now. That's it. let's move on. Yeah, let's do this one. There's one that I certainly want to do because there's a subtlety in there, but let's do one that is almost the same as this one, but just with a little extra step. Jacco would love this exercise. It says, suppose that you have a pi meson, so some combination of a quark and an anti-quark. It's an up and an anti-down. That's Jacco. These things, small particles, they radioactively decay, quantum mechanically decay into other particles, and they live for only a small amount of time, that time being given by 26 nanoseconds. The exercise says this happens on average, and I hope you understand why it is on average.
Because of uncertainty.
What uncertainty is that?
Quantum uncertainty.
Yes, thank you. So they say on average because a individual pi meson, you cannot with certainty say when it will decay. In classical physics, yes. Quantum mechanics, no. You can only talk about averages. It has nothing to do with our lack of being able to do good measurements. It's really built into nature itself by the Heisenberg uncertainty principle. This has nothing to do with relativity per se. So we're not going to bother about the average and this quantum mechanical nature of these things. It's in there, but this will complicate the issue without resolving the relativity. Okay, so what they say is, now suppose that you have a laboratory and there's a pi floating around in this direction with some unknown velocity v, and the question is, suppose that in a laboratory you see the thing fly for 10 meters before it falls apart. Question, how fast must it have flown? What has this value v been?
Can you repeat the...
Yes. They say, suppose that you create a pi meson, right? Jacco standing over here, shoots a couple of other particles against each other, a pi meson flies out. Pi meson comes out, flies with an unknown velocity v, and you see it go, and then 10 meters later you see it decay for quantum mechanical reasons. If you know that distance, let's not make it 10 meters, it's called d for generality's sake. If you know that the distance is d meters before you see it fall apart, how fast has the particle flown? What was v?
So you can find the time for us it takes to decay, and then because we know the distance for us and the speed is the same for us and for the meson, we can find the speed.
That's all there is to it. Absolutely. So in high school physics, I'm really bashing high school children right now, but I mean, I'm saying this as a point of reference, okay? If you didn't know about relativity, maybe that's how we should put it. If you didn't know about relativity, what you probably, or you might have done was say, oh, but wait a minute. I know that it traveled d meters, and I know that d, high school physics, is velocity times the amount of time that it flown, which maybe is this number. Then I know this one, 10 meters, I know that number, that's that. I can calculate, this is wrong in relativity. Because the disconnect is that this 10 meters is measured in this frame, whereas this number is measured in that frame. And those numbers in the frames, these numbers change. So this is exactly what you're saying. I mean, we have to convert the one number in the one frame to the other frame. Now, there's two ways that you can do this, by the way. You can say, you know what, I'm going to take this number, convert it to this guy's frame, and then calculate in his frame, high school physics. Or you say, no, I'm going to take this number as given, I'm going to change this number, and then do high school physics. Both of them are fine. Both of them will give you the same answer. But this exercise wants you to do the conversion from here to here. So let's do that. Tell me, what are the events? Just following my steps there.
Well, it appears and then it decays.
Yes. So the event is the creation of the particle. So that's Jacco standing here doing the work. And here is its creation. It's an explosion or something. Okay. And the distance between these two, that's d, and that's d measured in the laboratory frame. Let's identify the frames.
Laboratory and pion.
Sure. Okay, let's do that. The pion frame.
And the pion is the one that sees the events happening at the same location.
Yeah, of course, exactly. Because in his location, he gets created where he was, and he gets destroyed where he was. Okay. So great. So that means we now know this again. The double statement in one beautiful phrase. We know that we can use the formula, and we know which one of these two is which.
Yeah.
In fact, already by the notation you could tell, right?
Yeah.
This is why in particle physics they call lifetime tau, because it's always the proper time. So, let's do that. So that means that the amount of time that it takes before the particle falls apart, as seen in a lab frame, is gamma times the amount of time that it takes in the pi frame. So we can call this pi, something like that. And now it's just a matter of putting in the numbers. So let's do that. Well, we don't know the numbers because we don't know V. We don't know what gamma is. We just know that there is a gamma. This number we do know. We don't know this number, do we?
No. But we can actually get the unknown variable, let's say that the dt lab is the distance divided by the velocity.
Yes, exactly. Because this number, as long as we stick to the lab frame, we can use our high school physics again. Yeah. If you want to know how long it has lived, if you know how much meters it traveled in its lifetime, it's with a certain velocity, then this is 10 meters, yes, or what I called d before, divided by how fast it was going, which was given. What was it?
It wasn't given.
Oh yeah, of course, yeah, sure, it's this, yes. Yeah. But long story short, we know this number, it's 10. And we know this number, it's 26 nano. And all the rest of it is just a function of V.
Yeah.
So you can just algebraically solve V. There's no physics anymore, this is just doing the math. So yeah, the strategy that you suggested is correct. I found 7-9.
Yeah. It's quite hard.
So it's about 80% the speed of light. Now I'm going to be a little bit fussy here. No, there's a reason.
What?
No, there's a plus minus.
Because velocity is a vector.
Yeah.
That's
go the other way.
Yeah. There's two reasons: mathematical reason and there's a physical reason.
Because when they decay, no.
That's because you think about two decay products flying in out. Conservation momentum is what you're thinking of.
Yeah.
Which we will prove in lecture number 5. But no, that's not the reason. Because we're not looking at the decay products in the first place. No, it has to do, mathematically speaking, it has to do with that this gamma consists of a square root. So just if you do your algebra, you have to take the square root, and you know that the answer of a square root is plus or minus. So that's maths. But it also tells you something physically. It tells you, well, you tell me, what does it tell you, the plus minus here?
It doesn't mind which direction.
Exactly. You would see the same time dilation whether it was flying in that direction or in that direction. Now I'm going to take Robin's comment, because we are just talking about either this or this. But if you know that velocity is a vector, it could also have moved in that direction, that also is allowed.
Thank you.
So there's an extremely important physical message here, that apparently relativity does not care about in which direction things move. You will always find the same answer. I was talking with the other group about one of these Superman movies from the 1970s. If you've never seen them, go watch them tonight, this weekend anyway, right? After you turn your relativity. There is an exercise, there is a Superman 2, I think that it is. Superman finds that his girlfriend accidentally got some rocks on her head, and yeah, you know what I'm talking about? Yeah, you see this. So what he does then, I want to make time go backwards.
Yeah.
So he decides that means I have to fly in this direction around the Earth, so time will go backwards. Yeah. So some misunderstood version of relativity that if you go in one direction, time will slow down or dilute or whatever it does. So if you go the other way, you will go back in time. That does not happen. Okay? And here's why you see why.
CMS.
Yeah,
so.
Exactly.
I thought he was just going faster than the speed of light, so that's why it goes reverse.
But you can immediately tell that won't happen. If you go faster, you would think that if you go close to the speed of light, then the gamma factor goes to infinity, and strange things happen. And then you would think, so if you go past the speed of light,
time stop.
Well, it already stops if you go with the speed of light. So you think if time stops at the speed of light, so if you go faster, it will go in the other direction, right? You go to 0 and then you go to the other side. It's minus. No, it doesn't, because of the square root thing. You do end up with something. It's called tachyons, which is a whole world by itself. And if you never heard of that, forget about it.
Yeah, but we are not sure that tachyons exist.
But okay, that is very good. So you knew about tachyons.
Yeah, but they are considered, since they move faster, since they supposedly move faster than speed of light, their time is reversed.
Their time is reversed?
Yeah, like they have negative mass, like their mass is less than 0.
They get imaginary mass. Yes, this is not the same as negative.
I thought they had negative mass. Like their mass was considered to be negative. That's why they have, like, there is no proof that they exist.
Okay. There's a subtlety there. It has to do with the concept of relativistic mass. Short version of a long story. I know what you mean, but it depends on exactly how you have defined mass in this context. Anyway, that's this exercise. Okay. Easy enough so far, yes? Okay, let's make things a little bit more difficult. There's this beautiful exercise where they say something about it. This is, I think it's 410, let me check. 47, forget which one it is.
47 spaceship?
Oh yeah, no, I wanted to do 410. 47 is very similar, but it looks so much like the other exercises. I prefer to do 410. Alright, there we go. It says, the sun and another star are 60 light years apart. Now, you don't have to, but it's maybe good for visualization purposes to make a picture. So here's a sun, and here we have a star. And they are 60 light years apart and are at rest relative to one another. Now, that is an extremely important second part of the sentence for our understanding later on. What do they mean to say when they say they are at rest with respect to each other?
They move in the same reference frame?
Yes, exactly, the same reference frame. They are different locations in the same reference frame, but they are in the same reference frame. And it's going to be important later on. Okay, they also say they are 60 light years apart. That already is a suspect. See years? That's a suspect statement because, well, measured by whom?
Yeah, that's.
But
the same in the exercise.
Yes.
How do you your lights? Do we take in consideration when we make the measurement that, like, if it's just the definition, like, the time it takes a light to travel like that place, but do they take in consideration the fact that there is like contraction, and since it's very close to the speed of light, like
what is close to the speed of light?
I mean, if we wanted to take like the if we want to be very precise, we should use like the formula we use tau, but since like it's the light itself, like.
Oh, but wait a minute, we have to identify which reference frames we're going to look at, yes?
I know, but I mean, just in general, when they talk about, like, light years, like...
Yes, it's simply a distance. I mean, what you can think of is the amount of distance light has traveled if you gave it 1 year of traveling.
Yeah, but from which, like, that's the thing, do they talk...
Yes.
Is it from the light itself, or is it from...
It's from any other.
Okay.
Frame, and that's really the question. You don't want to look at how stretchy things are in the light system for reasons I will show you in a moment. So yeah, I mean, the way that we usually define light year is how much distance light has traveled if you give it 60 years of travel time. But then, in principle, in the definition, you can ask the question, yes, but is it the amount of distance it has traveled as seen by itself while traveling? And the answer is no. Okay. So there is some messiness, I agree, in how exactly you define it. And if you define a light year as well, it has traveled so many years, blah, 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 then you immediately think, oh, so it's the distance as he himself thinks that he has traveled. No, that's not the definition. You see light go, and that distance. You're not viewing it from the light itself. 60 light years. In the exercise, they mean as measured in this system, in the sun-star system. Now, we already saw that the second half of the first sentence tells you that this guy's system is also that guy's system. So it's 60 light years distance seen as well by the sun as it is by the star. Okay. We have a spaceship. This is, well, it's the best I can do. I'm trying to draw a flying saucer. There's a guy in here. Okay. And it says it goes with 4/5 of c in that direction towards this star. Good. To complicate matters a little bit, they say that there's something else going on. This guy travels from sun towards this star, and at the moment that he arrives at the star, something else happens as well. Somewhere along the way, the sun exploded. Sorry, that's the exercise. They say the sun explodes. Kind of a macabre exercise, but there you go. The sun explodes. So that means that the light of the explosion is sent out into space, including towards the star. So that means that this guy is happily flying along. The sun explodes somewhere in the meantime, sends out a flash of light. The light goes faster than the spaceship does, so the light will gain on the spaceship, and the exercise is set up in such a way that both the flash of light as this guy both arrive at the star at the same time. Can you see that it now becomes important to identify what the events are, because you can point at multiple events here. So let's go through this. What they ask is, exercise A is make a drawing of the situation. Now, okay, here's a drawing. Okay, they make it sound as if there is some practice in relativity to always make drawings in a certain way. There isn't. They want you in exercise A to do this so you have some visual idea of what happens. Let's go to the calculating part. Here's B. They say, when the ship arrives here, what does the star clock read? As in, what time is it at the moment that the ship arrives here? Let's do some identification. What are the two events that we're talking about here?
60 divided by
That is the answer, but let's go through the list. What are the events? You're right.
The ship starts flying.
One more time?
The ship starts flying from the sun.
Okay.
Oh, is it flying exactly from the sun? Like from the middle of the sun?
Okay. Well, at 60 light years, the radius of the sun is going to be negligible, yes, but you're right. So, yeah, the departure from the sun, that's an event. It happens at this one particular moment in time, at this one particular place, namely here at the sun. And yes, you can dabble, you know, think about it, well, how was it here or was it over there? Well.
Or does the light start traveling from the surface or from the sun?
They don't specify it. But then again, the radius of the sun is ridiculously small compared to the 60 light years. Yeah, so it's going to make it almost no difference whatsoever. But you're right, in principle they should, if you really want the 15th number somewhere behind the comma, then you need to specify it.
And the T0 when it starts?
This is a T0. Yeah. This is event 1.
And then the second is when either the light or the thing from there.
Yes, you're right. Let's go for the ship. The ship arrives at the star. Okay? So we have our two events. What are our two reference frames that we're going to compare between?
Sun and star reference. Sun star reference.
Yes. Okay, there you go. So here's one reference frame, which I'm just going to call the star and or the sun reference frame. And here's the sun frame. There you go.
No, the ship frame.
Yes, thank you. Yes. Okay, so this is how you make mistakes with them. Ship frame. There we go. All right. Now let's do some calculation. The question is, what time is it on board of the the star? What time is it on board of the star at the moment that he sees the ship arrive?
It's just the distance over speed.
Yes. Actually, it's what you said as well. Right? I mean, this is just your high school physics again. Yeah. He's going to stick to this frame. Don't bother about the other one. You say it has to travel 60 light years. Does so with this velocity. Divide these things to get them. So that means that delta t, so the delta t, the time between the two events as seen from the star, is 60 light years.
Like 75.
75, yes. Divided by its velocity. So that gives you 75 years. So that's easy enough. No relativity just yet. What does a ship clock read? Question. Same two events? Different events?
Different events. It's the same events.
No, it's the same events.
It's the same events.
Yeah.
It's the same events, but seen from a different reference system.
Yeah.
But it's the same events. It's still the departure and the arrival. Now, is there one of the two frames in which the two events happen at the same location?
In the ship frame.
Yes.
Yeah.
So that means that we are allowed to use this formula, and we know which of the two is the d tau. Which is the d tau? Is it the that's the d. Okay, so that's easy enough. So delta t star is gamma delta t ship. You know this number. Via v, you also know this number. Put everything in. And I thought it was 45 years.
No, it's the opposite.
Yeah.
We know
we want to find the
star,
ship.
and we want to find the time of the ship.
Oh yeah. So yeah, of course, yeah. So we know this one. We don't know that one, but we do know this one. Yes. So that gives you delta t ship. Now, before you do the calculation, bigger or smaller number than 75?
Smaller.
Is that by looking at the gammas, or is it out of
Logic.
logic? Yeah, tell me. What is the logic?
I mean, if it's moving, it's gonna have the time like the time.
Yeah, but listen, both of them are moving, right?
Yeah.
No, but gamma is a number that is bigger than 1.
Yes.
So the ship is going to be.
Yes. No. We're all seeing. We're all really saying the same thing. The easy thing to remember is this thing that you see in most books, and it's called moving clocks run slow. It means if you look at something happening that is moving with respect to you, you will see the bigger number.
Mm-hmm.
Okay.
That's
that helps you.
tricky to say, because if you say moving clocks run slow for who, it's very tricky to say. I would not see
But
the
this
logic
book
in that
says
sentence. That's a weird sentence. I would not remember it with that sentence.
What is the weirdness about it?
You say, what was the sentence again?
Moving clocks run slow.
You say moving clocks run slow while you observe the moving clock.
Yes.
But it could feel like the moving clock runs slow for itself, and then it's weird. You know, it's just how you hear it.
Well, for itself,
slow-mo is always a reference, so it's always compared to you.
Yes. So if you look at something that moves,
Yeah.
yes, then you will see that thing moves slow.
Yeah.
That's what I mean.
Yeah.
It's not if
I get
you
what
are
they
on
mean,
board.
but
If you're on board of that clock that is moving, well, in that frame, the thing is not moving. So there's. I mean, I agree. It's an incomplete. The statement is not extremely accurate. It might confuse you, but I mean, you do understand how this works, yes? So.
Yeah, I understand.
Yeah, but the way that phrase is typically uttered has some. There's ambiguity in there. Anyway, you go through this calculation. I found 45 years. So that's fun. That means that on board of the ship, it only takes 45 years to traverse 60 light years. Even if you're going slower than the speed of light.
you also solve this exercise with the other formula?
Yes.
The length contraction?
Yes. But we've now done, we have gone to the ship system, calculate everything. We could have also gone to the, very briefly put, what you could also have done is say, you know what? If this is some huge meter stick that in the star system is 60 light years wide, then the same stick would look from my frame, the ship frame, to be Lorentz contracted, a shorter distance. Yep. And therefore, if I have to fly a shorter distance with this velocity, I come out with a smaller number. And if you do that calculation, you will find the same 45 years. Okay. So just pick a reference frame, then apply either time dilation or Lorentz-contraction, depending on which one is appropriate, and you will always find the same number. Okay. Okay, now let's finish this exercise and then have a break. Namely, look at that. So this is fine, okay? This is easy. D. When the ship arrives, what does the sun clock read?
75 years.
Yes. That was that sneaky second part of that first sentence of this exercise, yeah? Remember that the first sentence said that the sun and the star are in the same reference frame? Yeah. That's code for you to understand that they are going to measure the same duration of time because of the same reference frame.
But why is it tricky?
Because they want you to believe that what you measure at the star as a duration is not the same as what you measure at the sun.
Basically, try on you to not pay attention.
Okay.
So
that's what all the exercises are about.
Yeah.
So again, the second half of the first sentence really just is really just a statement of this.
Yeah, but they're already told that they are like synchronized in the beginning. Since then, it's actually.
Yes, but that's because you're already seeing it. There might be people who think, oh, wait a minute, the sun is not the star. There are different locations, and therefore there's some sort of time dilation between those two as well. There isn't. It's a trick question. They wanted you to think that there isn't a difference between the sun and the star, and there isn't.
At the same time that the light to the star.
Okay. Now.
Yeah, but I was just like.
Yeah. I get it.
Final exercise, then we have a break. In the E exercises say, well, the sun has exploded at some point, and the question is, at what time? I should really read carefully because when the sun explodes, what do clocks on the sun, star, and the ship read? Now, we already know whatever the sun clock is going to read is also what the star clock is going to read. Okay, so same trick question. So we only have two reference frames to think about. How much time after the ship has departed from here will the sun explode as seen from the star? That's the first question.
That's 60 year from the star, which is if 60 year, if it's just like from the star without taking into account the ship.
Oh, wait. You say 60 years?
So so if I am at the star,
yes,
just look at the sun.
Yes.
The times that I see the light coming.
Oh, but yeah.
Until myself.
Yes, but that is not the question, is it? The question is not when do you see the sun explode. The question is when has it exploded. Remember that there was a difference between what happens and when you see it happen? They're asking when it happened, not when the light has actually arrived at you. Okay.
So I said that like when there's a point in time when the sun exploded and the ship was somewhere, then the time according to observer it takes for a ship to travel to the star is the same as the time for the light to travel to the star.
So if we take T0 as when it starts flying, at T15 years it explodes.
Yes, that's correct. Again, we don't have to switch between reference frames. What we can simply say is, well, listen, wait a minute, why is this 15 years?
75 minus
60.
Yeah. 60. That's 15.
I found something else.
What did you think?
I found 12 light years.
12?
Well, maybe that's from the ship. I'm talking about the sun.
Yeah.
From the sun it takes 75 years.
That was distance, sorry, that was distance.
For the spaceship to get there?
Yes.
I found that after 12 light years of traveling of the ship, the sun exploded.
So he's talking about the ship. I'm talking about like what the star reads.
So it takes 15.
Okay, so there's
15 from the star point of view is 12 from the ship point of view.
Okay, so we're talking very subtly about two different questions then, right?
But you asked the time of the star when the sun exploded, so that's 15.
Yeah. Okay. Well, that is the way that I answered the question. Listen, if it takes 75 years for this thing to go from here to there.
Yeah.
Yes.
Yeah.
And the light must have traveled for 60 years to get from there to there. Then the sun must have exploded after 15 years. No relativity there, though.
Yeah.
Right? So this arrives at the same time as that light arrived. This one took 75 years. The light took 15 years. So apparently 15 years after this one has left, this is when the light came out.
Yeah.
So that means that the moment at which the sun exploded, as seen in the star frame, is 15 years after the spaceship has left.
Yeah.
But note, and here's this part, the events have changed. Do you agree with that? Well, the two events now are the moment that the sun explodes and the moment
it arrived.
Yes. We have changed events. That is what I meant there. You have to be careful about these things. Yes?
I have one question. Why is it 75 years? Because here it says when the ship arrives, what does the star clock read? And it said before, just as the ship arrives, a light signal from the sun indicates that the sun has exploded.
Yes.
So that means it's 60 years. I mean, when the ship arrives there, the star sees the sun exploding.
Yeah.
That means the light took 60 years to reach the star.
But it didn't
so
explode
it took
at
the same time for the ship to arrive.
No, it's 75 years. We just calculated that.
Yeah,
the sun exploded
starts before the sun explodes.
Because like the light from the
The
sun
ship
takes
is flying is somewhere in the middle of the way.
The question is not when you see the sun explode, but at what time does the sun explode? So it takes 60 years to be able to see it.
Yeah.
But then it doesn't tell you when exactly it has happened. So you see it at 60 years, but you say, okay, there is a spaceship that goes with that took 75 years to come until my place with that speed. So if I see at the same moment when he arrived an event that should have taken 60 years to see it, I just subtract them, and the difference between the two is going to be like the moment. I don't know if I'm clear.
Okay, so at the year 2000 the ship starts.
Yeah.
At the year 2075 the ship arrives at the star.
Okay.
And we know that in the year 2075 also the light arrives there. So the question is, which year did the sun explode? And the answer is 60 years ago from this point when the light came to the star. So it's 2075 minus 60, so it's 2015.
Okay, that makes sense.
Yeah.
But
it's very important to get this straight. And we're all saying the same thing, but it's hard to get lost in these details. This is an extremely simple exercise, but you might think you pull all this relativity into things, so it's not necessary here. It simply literally says, I'm just going to explain, rephrase one more time the same thing, that the light takes 60 years to get there, yes? So at the moment that it arrives here, then you know that the sun has exploded 60 years ago, okay? But if the ship has traveled 75 years, then it means that there was 50 years in between the explosion of the sun and the departure of the ship.
Yeah.
That's all there is to it.
Okay.
Maybe now it's a good time for a break. There's one extra part to the exercise, we'll come to it after the break, yeah? So should we do, 10, 15 minutes or so? We can be in here?
10.
10, that's fine.
It's just been offered to the person.
Okay people, I propose we continue.
Yeah,
He said that.
Are we all clear on this exercise so far?
Yeah.
Okay.
Then we have
note. I've written down delta t sun.
Yeah.
I already had a delta t sun, which was it was 75 years, and now I write 15 years. What is the difference?
It's for a different event.
It's for a different set of events.
Yeah.
Exactly. Because this was the amount of time that elapsed on the star and or the sun between the departure of the ship and the arrival at the ship. And this is the amount of time that passed between the two events, the departure of the ship and the explosion of the sun. Two different events. That was my claim here. You could have in the same exercise all of a sudden events change. So there's that. Now the question is, okay, so we now know that the sun explodes 15 years after the ship has left the sun. Just as a test question, is that also when they see the sun explode?
No.
No, this is just when it happened. Then the light still has to travel its own way towards the star, and only then do they see it happen. But that is not the question. The question is not about travel time, it's about when it happened. Okay, next question. Ship. So what is the amount of time that passes on the ship when the star explodes?
So the ship is the moment where the event happened at the same location, like the explosion and the arrival to the star.
Wait. What are our two events exactly?
The explosion.
Yes.
And when he arrived at the star.
No. When he departed the star, when he departed the sun, and when the explosion happened. Now, for which, if any, of the two reference frames does it happen at the same location? It's the sun. It's the sun. Yeah, I mean the departure from the sun, or the departure from the ship from the sun, and the explosion of the sun happen at the same location in the sun frame. So that means we've identified that for our new two events, there is a reference frame at which they happen at the same location. So that means we are allowed to use this equation. And we now know which one measures the proper time. So you tell me, what should I write down now?
Yes, T sun
Gamma.
Yes, because the guy for whom the two events happen at the same location, which is the sun in our case, that's the person who gets the gamma, yes, according to time-dilation rule.
But then time on the ship will be bigger.
Yes.
But does it make sense?
Let's first calculate the number. It's a good question though. We know our gammas here, yes? And some number comes out, and I forget what it is, 25 I think that it is? Yeah? I forget what gamma is in the first place. 3/5 or so? 5/3. Okay, so we have to multiply 15 by 5. Life gets complicated now.
25.
It's 25 years. What do you know your question?
Why? Because like if we look at it, like the ship is moving fast, so for them, whoever's in the ship, the time should still go like slower. No, faster.
No, but we're looking at it from the sun. So the sun is moving from the ship.
Yeah, I know how we're looking, but
if we're looking from the sun, shouldn't it be like smaller?
Yeah.
Because it's moving, so we should. I mean, not moving, but
we
are looking like in reference to the star-sun frame reference.
No, I'm just.
The ship is moving.
Since the event, both of the events are on the sun. The sun is moving relative to the ship. So we kind of think that the ship is stuck and the sun is moving away from it.
That's correct. This boils down to the question who gets the gamma. You multiply the amount of time for whom the two things happen at the same location, that time gets multiplied by gamma. Now, it's exactly right. If you are at the ship, you see the sun move away from you.
Yeah.
So.
Oh, okay. And the event is the sun departure and the sun
exploding.
Oh,
yes.
But then if we look like when the ship arrives, it has 45 years. So, but that bit is like less than, you know, like if.
No, not yet.
Wait,
go ahead.
sorry. So it traveled only like 15 out of 60 distance, and it already has 25. Like according to this.
15, 60, I don't see.
Like the distance is 15 light years when the sun.
No. Ah, I see. I understand.
Different frames.
Yeah, exactly. I see exactly where the point is. I think her point is that, wait a minute, it has to travel a distance of 60 light years, right? And on board of his ship, already 25 years has passed, and it doesn't add up in some way, yes?
Yeah.
But as seen from the ship, does he have to travel 60 light years?
No.
He has to travel a shorter distance, a Lorentz-contraction. You haven't taken that into account.
Okay.
Yeah, subtle, isn't it? The big point in this exercise is that we secretly shifted to two new events, so that means the gammas all of a sudden got placed in different places. That's the whole idea here. By the way, this is the whole exercise. So there we go. Now, chapter 4 has many more of these exercises. Please do not wait for me to do this exercise. I mean, these exercises are all good. They train you in this way. They have some shifts of events and shifts of reference frames. It's extremely good practice to go through them. Don't wait for me to tell you. Just go through them. The odd numbered exercises have their solutions in the back. And there we go. Yes.
Can you do 4.4, because that kind of confused me, because it doesn't really say what time frame.
Yeah, sure. Okay, wasn't planning on it, but if people have nothing against it, there's 4.4. Is that okay? There is something that has to do with an epsilon there, and that I'm just going to replan for a moment. In chapter 5, I want to do an exercise where they use a trick with something that is an epsilon.
Yeah.
Okay, and I use that exercise not so much to show you relativity, but how to work with this epsilon thing.
Okay.
Now, on your suggestion, we can also do exercise 4, which is not a Lorentz contraction, it's still on time dilation, but it still has the same epsilon learning goal that we have there. So I haven't made this exercise beforehand, so I'm going to figure it out as we go along. Is that okay?
Yeah.
Yeah. I do want to do a Lorentz contraction exercise at some point, yes?
Okay.
But let's do...
But there will be one more with the epsilon, the one we were assigned to do.
Yes.
Yeah.
So,
like problem 5?
yeah, it's problem 5.7, I think that it was. Well, I mean, you tell me,
So
do we have a preference? We can do the 4.4, we can do one of the other ones. As far as the epsilon is concerned, both are fine.
Yeah. And he wants to go to the nucleus of the galaxy. How fast must he travel to go to the center of the galaxy?
Okay, let's do 4.4.
And the galaxy is like
Now, I have not worked out this exercise, and that means not that I won't be able to solve it, but it does mean that I don't know the numbers that come out. Okay. So at some point we have to put in some gammas here and there, and you will have to tell me either by calculating in your calculator in your hand what the numbers are. But sure, let's go. 4.4. There we go. 4.4. A space traveler with 40 years to live. That's a macabre kind of Star Trek exercise, but sure, why not? With 40 years to live, wants to see the galactic nucleus at first hand. How fast must the traveler travel? And then sure they have to say how far away we are from the galactic center. 8.5 parsecs, kiloparsecs. Okay. Here's some crappy unit conversion that we have to do at some point, but that's fine. 40 years to live, wants to see the galactic nucleus at first hand. How fast must he travel? It looks a little bit like this pion exercise that we saw, right? How fast did it have to go in order to traverse this 10 meters before it decays? That's pretty much the same thing. Instead of a pion, you have a guy, and he doesn't live 25 nanoseconds, he lives 40 years. But the question is the same. How fast does he have to go in order to traverse a particular amount of distance? So it's really the same exercise. So let's go through it. And yes, there is an epsilon issue there that is more important at this point, I think, than the relativity per se. Well, you tell me, what are the events?
Leaving. Bird.
Yeah, dying, yes. Let's make it a little bit more, less macabre. Let's say when he arrives at the center of the galaxy and sees the majestic beauty of it or something like that. And then he dies. Okay.
Yeah.
Okay, so two events.
When he arrives, he dies.
Okay. So that's the moment. That's the moment of departure, and that's a moment in time, but it's also a location in space.
The question is, how does he know how much he is left for him to live?
Yeah.
Maybe.
A bomb.
Yeah, that is a good question.
Alright. Program obsolescence.
Looks like some magic here.
Maybe it's in the future.
You are not allowed to leave more than.
Well, that's it.
There is too many people. So
this is like the movie Time, like that one. Yeah.
You have the time when you missed.
So instead of saying that the guy will
Die.
He's arrived at the majestic beauty of the galaxy. Okay, that sounds a little bit better. Okay, so he has 40 years. So those are the two events. What are the two frames?
The ship and the
This guy's
flying with
in
the
the
ship,
galaxy.
The guy in the galaxy.
Okay, so here's the center, and well, we can identify two frames: his own frame
and the galaxy,
and the galaxy. So this is really called the galaxy frame, and then this guy flying from here to there. That is what we call the I have no idea, the traveler frame or something like that. The traveler frame. There you go. So we have our two events, we have our two reference systems, and a number is given. So that's 40 years.
Yeah.
Whose time is that between the two events?
Traveler's
time, yes. So delta t traveler is given, and that's 40 years. And there's also a distance given.
Yeah.
So the distance between the two events, namely his departure and his arrival, at whose frame is that given?
Galaxy.
That's the galaxy. So we know that's the L of the galaxy, if you will, is, I forget what it is, well, it's called D. The distance as seen from the galaxy, that will be this distance, in the galaxy frame, is, here's this crappy number, 8.5, oh Jesus, okay. A parsec is how much distance a star would have to be in order for it to see it take a certain amount of angle as the Earth rotates the Sun. Right? If you look at it from this way and from that way, how far away you are, that gives you a measure of the angle. And there's a unit that's involved, but okay, there you go. 10 to the third parsec, and a parsec is 3.26 light years. So this is the number, and let's forget about the calculation per se. Some number comes out.
27,700.
Okay, there we go. Tell me again.
27,710.
What unit?
Light years.
So 27,000?
710. Light years.
Okay, I will trust you on this.
Times 10 to the power 4. Oh, okay, yeah.
Yes,
Yeah. Okay, yeah.
27,000, yes? So 2.7 times 10 to the power 4. Okay, good. All right. What do we do? Yes.
Maybe find the time that the traveler has in the galaxy frame, since we have, and we know that that multiplied by the speed should give us the distance that we have to.
This is really exactly the same as we did with the Pion exercise, yes. And just as then, we can make a choice. We can either take this distance, convert it to the amount of time here, and then do our high school physics in this guy's frame, or we take this number, calculate what it is in this frame, and then do high school physics in this frame. It will both give you the correct answer. Now, we are in the time dilation chapter, so I'm sure they want you to take this amount of time and put it into the galaxy's amount of time. I think that's what they want you to do. Again, both of them will work and give you the same answer. Let's go with this one. In fact, we can, as a check, do the Lorentz-contraction. We can also do the other one to see if we find the same answer. Yeah?
So but with speed, it's kind of not nice because it's like.
Okay. Okay. So we're going to use the time dilation. We're going to relate the amount of time that it takes to traverse the galaxy. And we're going to relate it to those two events seen by the traveler. So where does the gamma go? Yeah, it's not because I left the space open. I can still write 1 over gamma. So which one is it?
Because he's at two events at the same time.
Exactly. That's this trick over and over again. It's the traveler who sees him at the same position, his arrival, and seeing the majestic beauty of the center of the galaxy. So it's he who gets the gamma. But the gamma is unknown because we don't know what the V is. That's exactly your question. Then next step, and I just repeating the exercise with the pi. The amount of time that the guy has to live, as seen in the galaxy, is going to be the amount of distance that he has to travel. And we're now fully in the galaxy frame. So from here to what I'm going to write down, it's just high school physics because we're sticking to the same frame. So that is has to travel this crappy distance. And he does so while flying with a velocity of, well, unknown.
Yeah.
Okay. Equals gamma times delta t traveler. Now, from this moment on, it should be quite straightforward because the only thing you have to do now is calculate v. You know this number. You don't know gamma, but there's a v in there. There's a v in there. You can pry v out. There's no physics involved. Okay, so that's easy enough. But they want you to get used to a certain trick in relativity. It's a mathematical trick, so I'm not going to show you any more physics, but the trick is going to be important for later steps during this course. And I'm going to write it down here. Have you ever seen this before?
Oh.
No.
Nope. Okay. If you have 1 plus x, with x on number, and you multiply, or here you take the nth power of that combination, then it's about the same as 1 plus n times x.
Wait, so you have 1 plus x to 2 is 1 plus 2x?
Yes.
What does it come from? When x is very small.
Yes, you can only use this under the condition that n times x is small. This is a first order Taylor approximation, if you think of your calculus. Right? You take a function, you do first order Taylor approximation, and for this particular function it would look like this. And maybe if you know your Taylor functions, how that formula worked again, then you know that in order to find this number, you have to take this, take its derivative, that gives you n times 1 plus x, and then put x is 0 in.
Yeah.
That gives you this. And there you go. But it only works if n is much smaller, excuse me, n times x is much smaller than 1. Now how much is much smaller? Well, there's no critical number. The smaller it is, the better it works.
So the coefficient 1 plus, is it mx?
N.
So it's another number.
It's just another number.
Okay.
There's no physical meaning. This is a completely mathematical statement. It's nothing to do with physics per se. But why do they want you to use this trick? They want you to do this in the following way, and this is the mathematical part of the exercise, right? I mean, this is, the physics is solved. They want you to use this trick for the following reason, and that is that if you write V over C as 1 minus epsilon, the statement that you're making is that apparently V is very close to C, right? If V was C, it would have been 1, but it's a little bit less. So epsilon is a measure of how close you are to the speed of light. The smaller epsilon is, the closer you are to the speed of light. Now, what is one statement that you can make if you do relativity?
Limits. It looks like you want to
make it closer, like when we use limits to define how close, and when we make to see how, like, to calculate limits of a thing. I know we use the formula that looks kind of like that, so I'm just...
No, you're right, you're completely right. I'm making a somewhat stronger statement, and that is that you agree with me that this gamma factor, the Lorentz factor here, only becomes different than unity, different from 1, if you are close to the speed of light, yes? For the longest time, it will just be almost unity. And only when v gets very close to the speed of light, all of a sudden this starts to play up and it becomes 10, 20, 30, 40 or something like that. Okay. Now, that means if you're not going very fast compared to the speed of light, then this is almost 1 and you can just do your Newtonian mechanics. You don't have to worry about time dilations and such by very good approximation. But if we are going to do exercises where you're close to the speed of light, then by definition you're saying that epsilon must be a small number. Do you see that? So just us doing exercises where these formulas become important is equivalent to saying epsilon apparently is a small number. That's good news because that means we can use this approximation.
And the restriction of epsilon, is it given by the exercise, or do we decide, oh, we want it to be, like, we allow such, like, deviation?
That's completely user dependent.
Okay.
So suppose that you want to say, I want to know the answer, but I wanted to know between up to 1%. Then it's up to you to decide whether this is a good enough approximation. There's no rule there. I mean,
it's just like fixed depending on what we want.
Yes, exactly. Suppose that you want to do a measurement and the measurement is only accurate within 5%, then you know that your epsilon only has to be within 5% or so. It's user dependent. Now, my claim here is because you're doing relativity, in other words, because epsilon, because you're going to be close to the speed of light, that means epsilon is going to be a small number. And that means that this trick can be applied. And what they want you to see when you do this exercise is how much easier calculations become if you use that trick. Maybe not at first, because you have to get used to using the trick, but if you have it you have after some practice you see that this is much faster. Because look at this equation. It's a pretty crappy equation to solve. There's a v in there, there's a 1 over the square root minus v squared in there. It's not difficult, but maybe you can clean it up a little bit. So let's do that. That's what they want you to do in the exercise. So let's do it right here, right now. Let's look at gamma. So we're going to solve this equation, but we're not going to solve for v, we're going to solve for epsilon. Okay. Let's look at gamma first. Let's look at the whole left side first. Gamma is 1 minus v over c squared. And if I use this definition, this is equal to 1 minus epsilon squared. I haven't done anything, I just rewrote everything in terms of their epsilon. Look at this part, including the square. This one.
So minus 2 epsilon?
Yes. So you can very well approximate this thing by 1 minus 2 epsilon.
Yeah.
Oh.
Things become easier that way, don't they? So this is about, because we are making an approximation, this is about equal to 1 minus 2 epsilon. And then it's the square root.
But how do we get 2?
From the
approximation.
That equation there.
The n goes in front of the x.
Ah, that's m.
N.
It's the same letter.
Oh, this is what you thought that this n was a different number.
Yeah, I couldn't read it at first either.
Yeah.
Oh.
Okay.
Yeah, that's my crappy handwriting. My
No, it's
apologies. Now, so this is approximately equal to this, but because your relativity is probably going to be a good approximation. Now, this is not approximate equality sign, because from now on it's accurate again. 1 minus 1, they cancel each other out. Square root 1 over 2 epsilon.
Otherwise we'd have like 2 minus square epsilon. Like we just like love this whole thing. But since epsilon is very small to the power square, it's really gets really small. So small that we can like make it.
What you're saying right now is that you don't have to take into account the x squared part, because if x is small, then x squared is going to be smaller still, so you might as well leave it out. So, okay, there we go.
Yeah, that is.
So that takes care of this part. And we can also take care of that part, because this v is 1 minus epsilon times c. Okay? Now I'm going to put everything together. I'm going to call this d for now, because I don't want to write this number. And at the end you can put in the numbers if you want. So apparently this whole left-hand side of the equation that we have to solve
Is it not square root?
Which
1 minus epsilon. Like on V. Where you say V is equal 1 minus epsilon times.
No, this is correct.
Oh wait, no, sorry.
Okay. So this V is itself equal to 1 minus epsilon C equals, and we already saw that this is 1 over the square root of 2 epsilon times delta T traveler. I see another step we can make using the same approximation. Well, we don't even have to, by the way. Well, there's many ways that we can solve this.
We can also square everything on that.
Sure. Now I'm going to do your step. I'm going to do one step before that time.
Because it's 1 minus 2. But that number is so small that
I just reverse the fractions on both sides. Okay, now I want to solve this for epsilon because that is what they want you to do in the question.
I just have a silly question.
Sure.
If we have the C in the light years, can we just like kind of get rid of the C that we also have like here?
Yes.
So it just in terms of conversion, we have D, and instead of like expressing it in light years, just in years, and then we get rid of the C and we have only D over 1 minus sigma.
Yes.
Okay. Is it okay or?
That is okay. Yes. Okay, so we have to solve for epsilon. You can square both sides because you have to get rid of the square root. Now if you square this side, the right hand side, you will just get 2 epsilon over delta traveler. What happens if you square this? At the very least it will give you C squared over D squared, yeah? But what happens to if you square 1 minus epsilon?
No, same as what we had.
1 minus 2.
Yeah, 1. This is before, right? It's exactly this thing again.
Yeah.
So that will give you 1 minus 2 epsilon.
But we have to square also the time, right? On the denominator.
Yeah.
Yep. The delta T traveler.
What about it? Oh, yeah. Oh, sorry. Yes. Thank you.
Yeah.
Okay. Now, you can now easily get epsilon out. Okay. Now, you would think this looks almost as much difficulty as just solving the original equation completely. But we will later exercises, this really pays off. Where you have very big complicated expression with many V's over C's in there. If you then use this approximation, everything simplifies out. Because all square roots and all squares, all of them get replaced by a simple sum of something plus epsilon, which makes it a lot easier.
And at the end we don't have any more epsilons, right? Like they cancel out.
No, because you want to know what epsilon is, so you don't want it to cancel.
You want, so you will exactly know the value of
yes,
epsilon.
That's the idea.
Okay.
Because if you know epsilon, then put it back in, you get what your B was.
Good.
Okay. Now, the advantage of using these epsilons is not very big in this particular exercise, but for later it will become very advantageous. And again, it hinges on the idea that you use this approximation, which itself only holds if epsilon is small compared to 1, but it almost always is, because otherwise you wouldn't have relativity in the first place. So, I did not prepare this exercise. I don't know what the number is that comes out, but feel free to work this out for yourself.
I got a very small number.
Yeah, tell me what it is.
I got 692.
Well, epsilon should be done.
What is that in?
Well, epsilon should be dimension, should have no unit.
That's not epsilon, that's the speed.
And did you calculate by epsilon or did you just calculate?
No, it's just easier to do it the other way.
Yeah, I think so. Again, I don't know what the number is. You would have to look it up or just calculate it.
For epsilon should be
very small.
Probably pretty small number. Anyway.
Maybe the calculator will not be able to actually get it. We'll see.
Well, the number is not super important right now. The idea is that you know how the trick works. So either solve it completely with all the square roots and such, or you use your epsilon approximation. I promise you both will give you very close to the same answers. How are we on time?
Yeah. Done. It's just like one.
Good question.
It's one.
Okay.
Too bad.
Oh well.
Till what time is it?
That's a one.
Oh. Okay.
That means we haven't done a Lorentz contraction exercise.
But if we understood, like,
it shouldn't be too difficult. You know what I'm going to do? Well, I mean, we certainly talked about this. What we now did every time was we converted everything back. Guys. What we now did every time was that we converted everything back to one frame, so we can use time dilation. But you can use also the other trick to go to the other guy's frame, which will require you to use Lorentz contraction. Let me do the following. Of my worked out exercises, let me just put a couple of both time dilation and Lorentz contraction online by tonight. Yeah. So you can just check for yourself how that works. So, any questions?
No.
No? Everybody good? Okay. Now, next week, another layer of complexity I'm going to add on top of this. So, if you are a little bit iffy about how this works, feel free to take a couple of extra exercises, do the odd ones so you have the answers at the end of the book. See if you can work these things out, yeah? And follow this schedule, please. This will help.
Yeah.